Hi everyone, my name is Christian Puente, and I'm a product marketing engineer here at Texas Instruments. Joining me today will be Harold Parzuger, who is our systems manager for renewable energy. Today we'll be talking to you about the benefits of gallium nitride for solar inverters. Before we get started, I would like to encourage you to ask questions throughout the presentation using the Q&A box, where we will have someone to stand by and answer questions in real time. We will also be conducting a Q&A at the end of the presentation. So now, I would like to talk a little bit about the trends we see in the solar inverter market and how GaN can help to address those. Within the solar inverter market, we see the need for higher and higher efficiency, as well as the need to reduce the size of solar inverters, especially in residential microinverters. So how can TI GaN help to address these issues? What I'm showing here in this image is the TIDA 010933. Which is a 1.6 kilowatt microinverter based on TI GaN that Harold will be explaining in more detail in the next slides. But I just wanted to highlight that TI GaN can allow this microinverter reference design to reach an overall efficiency of 98%. And since GaN can switch at such high switching frequencies, this allows for smaller magnetics, further allowing for a 40% size reduction of the overall board when you're comparing it to an equivalent silicon design. So not only are you getting high efficiency, higher switching frequency for smaller magnetics and a size reduction, but you're also getting over 2 times the power density of equivalent silicon-based designs when you use TI GaN for your designs. And now I'd like to introduce TI's new 100-volt integrated GaN power stages. These devices can bring great advantages to the PV input stage of a solar inverter. Starting on the left-hand side with the LMG 2100 R044, this is an integrated GaN half-bridge device. On the right-hand side, the LMG 3100 R017 is a single GaN FET, also with an integrated gate driver. Both of these devices, along with the integrated gate driver, have some protection features and an integrated bootstrap, which I will go into some more detail in the next slide. The LMG 2100 is 4.4 milliohm, where the LMG 3100 is at 1.7 milliohms. This allows for flexibility for different power ranges. And you can see that the LMG 2100 is currently released on TI.com, and the LMG 3100 is sampling now and will be in production later this year. So now looking at the LMG 2100, you can see here a functional block diagram as well as the package, some features and some benefits. I want to point out some things here. First of all, you can see here this note, exposed GaN dies for heatsink. So the way that this device is laid out is that we have 2 GaN dies exposed on top of the package, which allows for optimal heat dissipation in your design. As the pins would be facing the PCB, you could place a heat spreader or heatsink on top of the device with a thermal interface material to maximize your heat dissipation. Additional features include the integrated gate driver, internal level shifter, and synchronous bootstrap diode. This ensures that power management is handled within the device, making sure the output of the gate driver is at the correct voltage for the high side FET throughout operation. This eliminates the need for any external circuitry to perform those power management features. And these devices also include protection features with an integrated UVLO. And now taking a look at the LMG 3100, you can see that this device is very similar to the LMG 2100. The key difference here is that the LMG 3100 is a single channel device with the integrated gate driver, whereas the LMG 2100 is a half-bridge device with the integrated gate driver. Both devices include the internal power management features and the internal protection features, and both are topside cooled packages, as you can see here in the image. So in summary, both of these devices are all-in-one GaN power solutions with the integrated gate driver and internal power management, reducing your overall bore space and reducing parasitic inductances from external circuitry. So now I wanted to talk a little bit about the benefits of using an integrated gate driver. And what you can see here on the right-hand side would be a discrete GaN with an external driver. As you can see here in the diagram, you'll have external inductances that are introduced by the PCB, as well as inductances from the driver and the GaN FET itself. So these external inductances would increase your overall switching loss, and Additional components would take up board space and increase design complexity. Whereas on the left, this is the TI solution with an integrated gate driver such as the LMG2100 and LMG3100. You can minimize your switching loop and maximize efficiency, allowing for faster turn on and turn off. As you can see here in this diagram, the switching loop is reduced significantly and also eliminates the inductances from the PCB by having the gate driver in the same package. So now I'd like to turn this over to Harold, who will continue to talk about TI GaN-based reference designs.
Thanks, Christian, for the introduction. I'm going to take over from here. Hi, everyone. My name is Harald Parzowa, and I'm a systems manager at Texas Instruments, and I will be talking about two reference designs we developed at Texas Instruments to prove that GaN will have benefit to solar inverter applications. And the first design I'm going to talk about is a microinverter reference design called TIDA 10933. Good. So let me start with having a look into how microinverters have been done traditionally. The microinverters being used on rooftops or on balconies had been all unidirectional, meaning electrical power generated by a solar panel when exposed to light was converted in a first stage from typical panel voltages in the range of 20 to 50 volt into a DC bus voltage, typically at 400 volt DC. Different configurations with one or even two or even four panels connect the individual DC boost stages. The power levels range from 400 watt for a single panel to 1600 and even more for a quad channel configuration. That means the power aggregated at the DC bus is summing up and is converted into AC power that can be fed into a single phase grid with 110 volt or 230 volt, and that is depending on which region in the world you operate the microinverter. All this is unidirectional from the PV panel side to the grid side. The topologies that have been used on this are very often current source inverters like flyback or push-pull configurations. Those are really low cost, but have the disadvantage that magnetics and electrolytic caps components are big, which drives the power density low, and overall these converters have a reasonable low efficiency in the lower 90% range. Now there is a trend in the market to combine solar energy generation with battery energy storage, which leads to a kind of a hybrid microinverter. During nighttime or when sunlight change is significant, it would be nice to have an energy storage system that can provide energy into a household when excess power is needed. Since the voltage and the power levels at each input are pretty similar for PV panels or for a 48 volt battery storage system, a bidirectional DC-DC stage at each in-output would allow to mix and match batteries and PV panels. Key difference to the traditional configurations is that you need a DC-DC to operate bidirectional to allow energy storage from the panel to the battery. And to allow that energy from the AC grid can be used to charge the battery, the AC-DC needs to be realized in a bidirectional fashion as well. Meaning this topology needs to change from a voltage to a voltage-controlled converter, VCS. The goal for the TIDA 10933 was to build a highly efficient bidirectional hybrid microinverter at a very high power density with low cost that it can be integrated into the chassis of a battery storage system. But using it as a converter on the backside of the PV panel is also possible, of course. Now a look into the block diagram of the microinverter. I would like to explain the operating principle of this. As mentioned before, we have configurable inputs and outputs. We have up to 4 PV panel inputs that can operate with a 400 watt panels at maximum current of 14 amp DC. This is a typical value for PV panels, and over 95% of the panels available in the market would meet this requirement. Each of the ports can be reconfigured to operate with a 48-volt battery pack with a charge and discharge capability of 400 watts maximum. On the right side, we see the connection to the grid with a plug outlet. The maximum power this converter can sink and source into and from the grid is 1600 watt. The design has been done in 3 stages. On the right, we see the 4 bidirectional DC-DC boost buck stages that can take the voltage, which is in the range between 30 and 60 volts, and convert this to an internal first bus voltage, which is set to 75 volt DC. The second stage is a bidirectional CLLC stage that converts from the 75 volt to the second DC bus voltage, which is set to 400 volt. This stage is a resonant converter with a transformer in the middle and has a full bridge on the 75 volt side and a half bridge on the 400 volt side. On the 75 volt side, we are using 2 LMG 2100, a fully integrated GaN half bridge device with 4.4 milliohm on resistance. On the 400 volt side, we are using 2 LMG 3522 650 volt rated GaN FETs with integrated driver and an on resistance of 50 milliohms. When operating from 75 to 400 volt, the LMG 2100 full bridge operates as a driver for the resonant transformer, and the 2 LMG 3522 are operating as an active synchronous rectifier. When we reverse the operation from 400 down to 75 volt, the 2 LMG 3522 operate as the driver for the resonant transformer, and the LMG 2100 full bridge operates as a synchronous rectifier. The third stage is a totem pole AC/DC realized with 2 LMG 3522 GaN FETs and 2 slow-speed MOSFETs. The GaN FETs switch at a frequency of 125 kHz, whereas the MOSFETs switch at the line frequency, which is typical for a totem pole converter. The design challenges are making each stage operate at high frequency bidirectional and still achieve high power density. Operating each stage at fairly high switching frequencies, which is possible if you use GaN FETs, allows size reduction of the magnetic components. Let me now show you a couple of efficiency measurements we have done on the TI-DA 10933. On the block diagram, you can see the complete inverter again. When we look at the first stage, we can see the following efficiency versus input power applied from the panel. The 3 different graphs represent different input voltages to the DC-DC boost stage. You can see over a wide range the efficiency is way above 98%, even for low input voltages of only 30 volt. It has to be kept in mind that 400 watt panels, which are typical for residential use case, have a fairly constant output voltage around 33 to 35 volt. Since a PV panel is a current source for which the current changes mainly with light exposure, the assumption to operate between 30 and 40 volt is pretty accurate. And this stage has a very flat behavior over output power, which is very good. There is a definition for weighted CEC efficiency, which takes certain coefficients at certain percentages of power levels and sum those up. The calculated weighted CEC efficiency for this stage is around 98.6%. When we look into the complete quad boost stage, we see the effect of the DC-DC boost stage plus the CLLC stage combined together. As can be seen in the chart here, the curve is well above 96% over a very wide range. And here the calculated weighted CEC efficiency of that stage is around 96.5. For the totem pole, we see the efficiency graph in the top right corner. The efficiency of this stage is close to 99%. The calculated weighted efficiency is around 98.7. And if we combine all together for the complete converter, from DC to the AC output, the weighted calculated efficiency is over 95%, which is remarkable for a fully bidirectional converter compared to low-cost unidirectional current source inverters that achieve only lower 90% ranges. Let me talk about a few highlights of this reference design. We have been building this design in two boards, an AC-DC board and a DC-DC board. The total size for the two boards is as low as 20 by 20 centimeters. This is again very remarkable for such a huge feature set. The complete converter is controlled by a TMS320 F280039C control card from TI's well-known C2000 microcontroller family, which provides a lot of functions tailored for digital power control. All 18 PWM signals, as well as all the current and voltage feedbacks to close control loops on all stages, are handled by the F280039 in a single chip controller. The MCU is referenced to PV ground, which is optimizing the number of isolated feedbacks from high voltage side to low voltage side. There is no need for huge electrolytic caps on the DC bus voltage side because of the chosen architecture. This is impacting the size of the solution in a positive way. In traditional CSI converters, there would be a huge bank of electrolytic caps needed on the PV side to compensate the ripple on the AC side. Since we moved to a voltage controlled converter, the caps are shifting to the AC side, and since voltage is much higher, ripple currents in turn are smaller, and that is impacting the size of the electrolytic cups in a positive way. We are operating the GaN devices at high switching frequencies. As said, the AC-DC is switching at 125 kHz, driving the size of the AC line inductor small. The DC-DC input stage is operating at 250 kHz, which allows really small sized boost inductors at the input. And the CLLC stage switches at 500 kHz fixed, which helps to choose a small size transformer here. All this is impacting the size of the solution in a very positive way. And we had been able to achieve a power density on this design of 1 kilowatt per liter. This is remarkable since existing unidirectional solutions are achieving barely 300 to 500 watt per liter. And as you can see on the picture, the design has a heatsink on the back side. This is possible since all power devices are located on the back side of the PCB and are topside cooled. With this, the casing of the top side does not necessarily need to be made out of a metal. It could be plastic cover, which is impacting again the overall cost of the microinverter in a positive way. Last but not least, here is a summary of the key specifications for the design in a tabular form. After introducing the microinverter reference design, I would like to switch to another reference design we have been developing to demonstrate the benefits using GaN in solar inverters. This design is a single-phase string inverter reference design named TIDA 10938. The TIDA 10938 is again a hybrid solar inverter design. We see on the bottom right two PV string inputs capable to operate each PV string with input currents up to 14 amp DC. The maximum open circuit voltage at each of the inputs could be as high as 500 volt. That voltage would only be visible when the strings are not loaded. In residential use case, we very often see 400 watt PV panels. And typical maximum power point or maximum power point tracking voltages of those panels are 33 volt, meaning if we have 10 panels connected in series, the voltage present at the input of the DC-DC boost stage would be around 330 volt. With 10 panels, this means also as high as 4 kilowatt in a maximum power condition. For two string inputs, we are at 8 kilowatt. We rated this design for 7.2 kilowatt, but we will see later in the presentation that actually 8 kilowatt on both PV string inputs can be achieved with safe margin. All of the outputs of the DC-DC boost stages are connected to a common DC bus that is rated to work at 400 volt nominally. The second building block we have in this design is a bidirectional DC-DC stage that is connected to a battery pack that can range from 80 volt up to 320 volt, but also 400 volt would be possible since the DC bus voltage is nominally 400 volt, but could be higher. The currents to charge and discharge the battery pack is rated for 13 amp max. So for a 240 volt battery pack, this would translate in a maximum charge and discharge power of 7.2 kilowatt. Again, we will see later in this presentation that this design has safe margin to this. The third building block is the bidirectional AC-DC. It is rated for single phase 3.6 kilowatt only. The reason that we limited this output current in the single phase application to 16 amp RMS. And at 230 volt RMS, this translates to 3.6 kilowatt. So let me now deep one level deeper into how we partitioned this reference design and how we implemented the different stages. On the left, we can see the string DC-DC boost stages. They are realized with the LNG3522 30 milliohm GaN-FET device from TI with integrated driver. The diode is a silicon carbide Schottky diode. And since the control MCU is referenced to the negative bus voltage, the string current can be measured with a INA 181 across a shunt resistor in the negative rail. The voltage measurement on the PV string is also non-isolated. The boost stage operates at 120 kHz. It is important to notice that the inputs of the GaN modules with the integrated driver are non-isolated and are driven by logic buffers only. I want to highlight in general that this complete design has been trimmed for a total low system cost and avoids isolation wherever possible. In the middle, we can see the bidirectional DC-DC for the battery port. It has been implemented as an interleaved stage, which means the two branches of the converter are operating in 180-degree phase shift to each other. Each leg operates at 60 kHz, which results in a 120 kHz operation for the two interleaved legs. On that stage, we are measuring the boost inductor currents with the isolated amplifier AMC1302, which can be easily supplied from the GaN devices on the top of each leg. There is no additional isolated supply needed for those. The inputs of the upper devices are isolated. TI's digital isolator ISO 6741 has been used to drive the inputs of the LNG3522. The isolated supply was realized with a simple transformer push-pull stage using a transformer driver IC, the SN6501. And on the right side, we see the AC stage. Here we decided to build a configurable AC-DC stage. There are three possible modes of operation. You can operate it in full bridge configuration in unipolar PWM modulation, as a full bridge in bipolar PWM modulation, and as a configuration with a Herrick 6.2. All these different configurations have pros and cons, and we wanted to give in this design the flexibility to have one AC/DC stage that can operate for comparison reasons in 3 different modes by changing the software and applying different PWM modulation schemes. It can be said that the Herrick operation provides the highest isolation from the panel to the AC side. This is important because any parasitic voltage buildup at the panel side can cause a ground fault DC current on the AC side, which would trip the converter. And that's why a good common mode rejection into the AC/DC stage is very beneficial. The full bridge operation with bipolar modulation offers the second best common mode rejection and is also a good choice for a string inverter application. After explaining the block diagram, let's have a look at how the efficiency looks like on all the different stages. We are starting here with the DC-DC boost used on the PV strings. The schematic in the middle illustrates as well which block we are looking at. In all shown measurements, the DC bus voltage was set to 400 volt DC. The switching frequency of the up converter has been set to 120 kHz. On the top left, we see the efficiency versus output power into the DC bus. It can be seen that the converter operates well with as low as 50 volts at the input. With the limitation that the input current is only 14 amps, we see that the output power is only 700 watts. It can be seen that the efficiency is already in the range of 96%. With increased input voltage from 150 to 200 volts in 50 volt steps up to 350, we achieved output power increases gradually up to 4.9 kilowatt for just one PV input. The efficiency is really remarkable at 99%. Clearly showing the benefits of GaN in that application. And on the top right, we just see the same graphs, but versus the input current, to see that the efficiency is very constant over a wide range of input current. The input current that we have been choosing is pretty much matching the behavior of a PV panel. On the bottom left, we see the temperature profile we derived during the efficiency measurements. It has to be noted that the LMG3522 has an integrated temp sensor which allows to report of the actual temperature measured at the junction of the GaN device out to a MCU for monitoring purposes. It can be seen that the temperature inside the GaN device is not exceeding 70 volts, which gives a lot of thermal margin to the design. To get information about the thermal behavior of the cooling system, we measured the heatsink temperature at the indicated location here with the temp sensor ICs. The heatsink temperature is not exceeding 40 degrees, even at full load, which demonstrates the robust cooling concept of the design. The same temperature measurements have been done on the Schottky diode as well, to see if any critical condition is happening. The next slide shows the bidirectional DC-DC for the battery port. The schematic in the middle illustrates again which block we are looking at. In all shown measurements, the DC bus voltage was again set to 400 volt DC, and the switching frequency for each leg was 60 kHz, which is resulting in a 120 kHz operation for the complete converter. On the top graphs, we see again efficiency versus output power into the battery for the buck mode, meaning we are showing a charging of a battery. On the top right, we see the efficiency versus charging current, which goes up to 30 amp. On the bottom, we see the reverse operation, meaning in boost mode, or in other words, a discharge of the battery. On the left, we see the efficiency versus discharge power, and on the right, we see efficiency versus discharge current. it can be seen that the efficiencies are very constant and above 98.5% over a wide range. Even at low battery voltages for only 80 volt, the converter shows around 97% of efficiency for charging and discharging, which is a very impressive behavior, which goes back to the low conduction and switching losses of the GaN devices when running at fairly high operating frequencies. I also want to mention that the measurements on the maximum output power had been limited to our measurement equipment that we used. Given the graphs and the temperature we have seen during the measurements, we feel very confident that this converter can achieve 9 kilowatt charge and discharge into a battery that is rated for 320 volt. And now, after a lot of performance measurements, I want to get to you some reference design highlights for the TI-DA 10938. This complete design is shown on the picture on the right. The design is partitioned into an AC-DC and a DC-DC portion, and the total solution size is 29 by 28 centimeters. All control algorithms for the DC-DC boost, bidirectional DC-DC, and configurable AC-DC are run on a TMS 320 F280039C microcontroller. We had been using again a control card that plugs into the main board, and the MCU is referenced to the negative supply of the DC bus. Because of the architecture used and the switching frequency is fairly high, which is possible with GaN, the need for huge electrolytic blocking capacitors is not that much. Running the GaN devices at high switching frequency allows also to use small-sized magnetic components, which in turn drives the total solution size down and allows for a high power density. And in the table, you can see all the specifications for the string inverter for all the subsystems. Comparing this converter to existing solutions out there with traditional implementations in silicon FETs, this design has a pretty much unprecedented efficiency at this power density at the power levels defined for this system. Let me conclude the presentation here with a short summary. Microinverters and string inverters are trending towards bidirectional operation and higher power density with smaller, lower cost passive components. The GaN technology enables bidirectional topologies and increases power density and efficiency at equivalent cost to silicon MOSFET implementations. And TI's GaN's integrated gate driver plus over temperature and short circuit protection allows a really simple system integration. We would like to thank you for joining this webinar and giving us the opportunity to introduce to you the benefits of GaN in solar applications.